So Gaussian elimination refers to using row operations to reduce a matrix to reduced row echelon form, and then using that reduced and simpler form to write down the solution set. We saw before that the only possibilities are that there's 0 or 1 or infinitely many solutions for a linear system. So we'll go through all three cases so that you can see what they look like and how to recognize them. For the moment, we'll consider the case of an example that just has a unique solution. Okay, so suppose that we've got this system as written right here. The very first thing to do is to go ahead and write this into augmented matrix form. So our coefficient matrix is 0, 1, 7, 1, 0, minus 1, 0, 0, 2, and then this is augmented with the constant vector 11, minus 2, and 2. Okay, and I'm going to shrink that down just a touch so that I can fit a little bit more on the line. So let's see. So I want to put this into reduced row echelon form, and for that I usually work from left to right. So I would start by looking at this column and figure out what needs to be sorted out. And I like the look of this 1 right here. I can use that as a pivot. So I'm going to move that up to the top. So for that, I would say, okay, so let's do a row swap. And the result of that operation would give me 1, 0, minus 1, minus 2, 0, 1, 7, 11, 0, 0, 2, 2. And at this point, I can see that I've got an upper triangular matrix, and so this is on the left side, anyways. And so that's always a great thing. That indicates that you're making good progress towards being in reduced row echelon form. I note that this 2 is going to have to go, so I might as well go ahead and take care of that now. So I'm going to have the 1, 0, minus 1, minus 2, 0, 1, 7, 11 part stay exactly the same, and then I will multiply 1/2 against row 3, and that'll get me 0, 0, 1, 1. And now I have exactly a pivot in each of the columns of my coefficient matrix. And so now I need to say OK. To get it in reduced row echelon form, I want it to be the case that each pivot is the only non-zero entry in its column. And for the first guy, that's true. And for the second guy, that's true. And for the third guy, it's not true. I'm going to have to get rid of each of these characters right here. So let's do some more row operations. And I'm going to have 0, 0, 1, 1 stay the same because I'm sort of using it as my tool for manipulating the other rows at this point. And to get rid of the -1 in the first row, I'm going to add 1 copy of row 3 to row 1. And to get rid of that 7, I'm going to go minus 7 times row 3 to row 2. So let's see. So that'll give me 1, 0, 0, and minus 1, and then 0, 1, and then when I subtract 7, I'm going to get a 0 here, and when I have 11 minus 7, I'm going to get a 4 here. So now if I convert this system back into a series of equations, the first equation says 1x1 plus 0x2 plus 0x3 is minus 1, and the next one says 0x1 plus 1x2 plus 0x3 is 4, and the last one says 0x1 plus 0x2 plus 1x3 is equal to 1. Now obviously there's a whole lot of unnecessary garbage there. What we really have is x1 equals minus 1, and x2 is equal to 4, and x3 is equal to 1. And I can just basically read that off from that last matrix. I just wanted you to be sure that you could see where it all was coming from. Notice that in the case of a unique solution, it turned out that in the reduced row echelon form, we got the identity matrix right here. This is not a coincidence. Whenever the reduced row echelon form of A is the identity, then there is a unique solution.